Today we'll be finishing off our discussion of Chapter 10, considering fluid dynamics. So up till now we've been considering stationary fluids. Here in the last couple sections of Chapter 10 we consider fluids in motion, and there'll be two equations that we'll be deriving that we'll be wanting to become comfortable with in fluid dynamics. So fluid flow, which is fluid dynamics, can be very complex, as you can see in river rapids and also in the swirling flames of a campfire. But some situations can be represented by a relatively simple or idealized model. Our treatment will be focused on the consideration of an ideal fluid who is incompressible and has no viscosity, that's no internal friction, and experiences laminar flow. So here are the two pictures, turbulent flow, where you have the fluid flowing generally from the left to the right, but it is swirling along the way, not flowing in straight lines. These are eddies, and it results in a loss of energy as the fluid heats up here. This is laminar flow, where the fluid all flows along lines directly from the left to the right. And that will be what the approximation will be in. So the derivation of the first equation is our equation of continuity. So here we consider an ideal fluid flowing along a pipe whose diameter is changing. So the fluid is coming in here from the left, flowing to the right, coming upon a cross-section of pipe area A1, and then narrowing down as it flows into a smaller section of pipe, cross-sectional area A2. Now the mass of the fluid does not change as it flows. Thus, as a mass m flows a distance x1 in this larger part of the pipe, an equal mass m must flow a distance x2 along the thinner end of the pipe. So conservation of mass says m1 over the time it takes mass 1 to flow that distance x1 must be equal to m2 divided by the time to flow that distance x2. The masses m1 and m2 are equal, so we can just write that as m. Re-expressing m1 as mass and as density and volume, m1 can be re-expressed as rho 1 v1 per unit time is equal to mass 2 can be expressed as rho 2 v2 per unit time. Now these volumes can also be re-expressed in terms of the area and the distance flow. These are just cylindrical volumes here. So V1 is just A1x1 and V2 is just A2x2. And substituting those two volumes into these equations, we then get rho 1 A1x1 over T is equal to rho 2 A2x2 over delta T. And then defining x1 over delta T as the flow speed at point 1 and delta x2 or x2 over delta T as the flow speed at point 2, then we can write down rho 1 A1 V1 equals rho 2 A2 V2. This is the equation of continuity for a compressible fluid. If it's incompressible, then the density isn't changing, and that means that rho 1 and rho 2 are the same. Thus, they'll cancel on either side of the equation here, leaving us with just A1 V1 is equal to A2 V2. And this is going to be the equation we're going to be using for the idealized conditions, incompressible fluid. Derivation of the second equation, a little bit more complex. It's Bernoulli's equation, published by Daniel Bernoulli in 1738. Here again we consider an ideal incompressible fluid. The fluid is again flowing in from the left to the right, and you can see it's actually not only changing diameter as it flows, but it's also changing height as well. So we're considering a volume that's enclosed from P1 to P2, and as that volume of fluid flows to occupy P1 prime to P2 prime. So you can see I've drawn shaded for the region initially occupied by the volume, and then a dotted volume for that fluid as it's flown along the pipe. The work energy theorem that we learned back in Chapter 6, a very important concept for us that we'll be using over and over again, says that the net work done on any entity is equal to the change in the kinetic energy of that entity. So what work is done on this section of fluid as it moves from occupying the volume P1 to P2 to the new volume P1 prime to P2 prime? Well, we know for sure gravity is acting as we are moving the fluid contained in this volume right here all the way up to this volume right here. Notice that this actual middle section right here doesn't change height at all. But anyway, we are lifting the fluid from Y1 to Y2. So gravity is doing work. And then the fluid ahead of this section and behind the section of fluid are also doing work on the fluid. So there's fluid back here that's not contained within the volume we're considering that is pushing directly forward on our fluid. And then there's fluid that is already ahead in the pipe over here that is pushing backward on this section or this volume that we are considering. So these are called pressure forces. Note that these pressure forces are non-conservative and that gravity is a conservative force. So the equation we can write then is that the work done by gravity plus the work done by pressure forces is equal to the change in the kinetic energy that the section of fluid experiences. Now the work done by gravity is equal to the force exerted by gravity, which is of course mg, times the displacement, and that displacement is just the vertical displacement, y2 minus y1. This minus sign comes from the fact that the angle between the force of gravity and the displacement is 180 degrees, and cosine 180 that comes from our work equation is -1. Okay? Again, I want to note that this mass right here is the mass that's being lifted. So this mass contained between P1 and P1 prime is the piece that's being lifted up here to the volume contained between P2 and P2 prime. Note again that this region right here is not changing speed, and it's also not changing the vertical position. Okay? So now let's calculate the work done by the pressure forces. So the work done by the pressure force is going to be equal to the force being exerted by the preceding fluid, and it is in the direction of the displacement. So again, that's the force exerted by the fluid here, and it's pushing along the distance L1. So the angle between the displacement and the force is 0 degrees. The other pressure force we're getting here is the force being exerted by the fluid further along in the pipe. So this fluid that is further along in the pipe is pushing backward on this section of fluid that we are considering, and so the displacement, which is to the right, and the force being exerted by that fluid ahead is to the left, and so we get the negative sign here for the work done by that fluid that is further along in the pipe as it's pushing backward on that volume. So if we come back to our equation, plugging everything into our work equation, we have minus mg times y2 minus y1, that's the work done by gravity, plus the work done by the pressure force, that's this expression, F1L1 minus F2L2, is equal to the change in the kinetic energy. So that's 1/2 mv2 squared minus 1/2 mv1 squared. Again, note that the only mass being lifted and changing speed is that contained in this volume P1 to P1 prime right here. So again, this is the only one that's changing speed and changing height as it is being moved over to this section of the pipe. So we can re-express the force in terms of pressure and area. So F1 is equal to P1A1 and F2 is equal to P2A2. And so we can, let me put the 1 and the 2 on here because it looks like I omitted that so that we're sure to keep up on all the stuff. There we go. Okay, so the volumes A1, L1, and A2, L2 are equal. So again, coming back to our picture, this volume right here this volume contained between P1 and P2, or P1 and P1 prime, is equal to the volume contained between P2 and P2 prime, because this is an incompressible fluid. So we're just going to let A1L1 equal A2L2, which they do, and just call that V. They are the same volume. Now substituting those into our equation, we now have this expression, minus mg y2 minus y1 plus p1 a1 l1 minus p2 a2 l2 equals 1/2 m v2 squared minus 1/2 m v1 squared. Now dividing everything through by v simplifies our equation. You see here you get m divided by v, which is just the density of the fluid, times g, y2 minus y1, plus, when we divide P1, A1, L1 by V, the A1, L1 cancels the V, we get P1. Likewise, with this next expression, we just get P2, is equal to, dividing these two terms by volume, we get mass over volume, which is density. So here's the new form that we have. Now rearranging our equation a little bit, we see that we get P1 minus P2. This is the work done by the pressure forces per unit volume, is equal to 1/2 rho V2 squared minus V1 squared. This is the change in the kinetic energy per unit volume, plus rho g y2 minus y1. This is the change in the potential energy per unit volume. So this is the work done by the non-conservative forces is equal to the change in the system's mechanical energy. So very familiar expression, and this is Bernoulli's equation. Note that P1 and P2 must both be expressed as absolute pressures, or they must both be expressed as gauge pressure. In other words, you have to have them both in the same form, either both absolute or both gauge. Now let's apply these fluid dynamic equations to a problem. So I'm not sure if you can see the text on this problem, but I'm going to read it for you, and then I've defined all of the quantities off to the side here. So let's go ahead and carefully read over it. So applying fluid dynamics equations, what it says here is water enters a house through a pipe with an inside diameter of 2 centimeters and at an absolute pressure of 4 times 10 to the 5th newtons per meter squared. So here is where it's entering the house. Right here it's labeled 0.1. A 1 centimeter pipe leads to the second floor bathroom, which is 5 meters above. When the flow speed of the inlet pipe down here at the bottom of the house is 1.5 meters per second, find the flow speed, pressure, and volume flow rate in the upstairs bathroom. So these are the three things that we want to find. So right here again, I always define everything over on the left, and I want to make sure that we distinguish between these 1s and 2s. Let point 1 be the inlet pipe right here that's coming from the ground, and point 2 be the upstairs bathroom, and let's set y1 equal to 0. So y1 is 0. The diameter of the inlet pipe is 2 centimeters. The pressure at the inlet pipe is 4 times 10 to the 5th newtons per meter squared. That's the absolute or total pressure. The speed there at the inlet is 1.5 meters per second. The diameter of the pipe upstairs at point 2 is 1 centimeter. It is located 5 meters above at location Y2. We want to find now what is the flow speed at point 2, what's the pressure at point 2, and what's the volume flow rate. Okay, so we have an incompressible fluid, so that means the equation of continuity that we'll be using is A1V1 equals A2V2. Note that this A1V1 is also the volume flow rate. Just check out the units. Remember, dimensional analysis is pretty powerful. So A times V is meters squared times meters per second, which is meters cubed per second, and that's of course volume per unit time. So the equation of continuity actually does give you the volume flow rate. So From the outset, we can immediately calculate the first thing we want, which is V2. We know everything in the equation of continuity except for V2. So rearranging V2 is equal to A1 over A2 times V2, and going ahead and writing the areas, which are just circles, we get that V2 is equal to 6 meters per second. So the second question we want to answer is, what is the pressure upstairs? Shh. What is the pressure upstairs? So we use Bernoulli's equation, which says that P2 is equal to P1 plus rho g y2 minus y1 plus 1/2 rho v1 squared minus v2 squared. We have everything defined over here on the side. Just plugging in, we find the pressure. Again, this is the total or absolute pressure, 3.3 times 10 to the 4th newtons per meter squared. Note that if instead we had been given gauge pressure here for the inlet pressure, then we would have been solving for the gauge pressure at the bathroom sink. Part C, now we want to find the volume flow rate. That's just the area times the flow speed. And so we are first of all going to check A1, V1. Plugging in all of the numbers, we can see the volume flow rate is 4.7 times 10 to the minus 4 meters cubed per second. And just simplifying that, that's 0.47 liters per second. We'll just check to ensure that we can calculate the volume flow rate as A2V2, and we come up with an identical answer. So you can see that as long as you know the cross-sectional area and the flow speed of the incompressible fluid at any one point, then you know the volume flow rate at all points. And that's a nice application of the equations. So thank you very much.